Hello everyone. So welcome to General Physics 2. So welcome to General Physics 2. So in this General Physics 2, we're going to discuss three parts. So the first part we talk about is optics. The second part is electricity and magnetism. And the third part is modern physics. So in the first part, we'll mainly differentiate optics into two parts. One is called ray optics. The other is called physical wave optics. Ray optics is also called geometric optics. Wave optics is also called physical optics. So in electricity and magnetism, we're going to discuss two parts again. So we'll talk about electrostatics and we'll talk about electricity in general, current or electrodynamics. And we'll finally talk about magnetism and end with electromagnetic induction. And finally, in modern physics, we'll discuss two parts. One, we're going to discuss atomic physics. And number two, we're going to discuss nuclear or subatomic physics. So let's start with the first chapter, geometric optics. So the name itself says ray optics or geometrical optics. So the primary assumption we consider is, in this chapter we consider light to be a ray, or you can consider it to be a straight line basically. So it has a straight line path. The reason we consider it this way is because it suits the macroscopic assumption of a wave. So because it suits the macroscopic assumption of the wave, we consider that it should to be a straight line. Now, why should we consider it to be a straight line? Macroscopic assumption of light wave. Why is it that case? If you look at a wave in general, a wave looks somewhat like this. So where it has crest and trough. But in general, when you look at this, we call it the wavelength, lambda. When you consider this lambda, generally for light, for lambda, the visible light ranges from around 0.4 to 0.7 nanometers. So this is really small. So when you consider that it's taking about that much time, it's micrometers. So if it's taking that small of a light, if you consider the wavelength to be that small, that's really small. That's about 1,000 times smaller than the human hair. So which means that you're basically dividing 1 millimeter into 1,000 parts, and even that would be smaller than, even that would be larger in comparison to the wavelength. So because wavelength is so small, what happens is when you consider the light wave to be somewhat like this, where you're having a basic, a light wave that's continuously rigid like this. In the macroscopic view, if you look at it from far, it generally suits the assumption that it looks like a straight line. Because the amplitude is so small and also the wavelength is so small that the wave in itself is not visible to the human eye. But it doesn't mean that what we see is a straight line. Because it's not visible to the human eye and because the wavelength is so small, when we consider the actual general understanding of how the light waves generally work, we can assume that this can be considered to be a general ray. So because we can consider this to be a general ray, we can use the assumption that, okay, this is a general ray, and we can, the easiness of making it a ray is that it makes it easy for analysis. It makes it easy for analysis, and especially it also makes it easy to understand the phenomenon. So understand the phenomenon of light. So light in general has some specific properties. So these properties come from the idea, one, the box. So let me list some of the properties. The first one is the property of reflection. The second is the property of refraction. Third is the property of interference. Fourth is the property of diffraction. And number 5 is the property of polarization. One nature of light cannot explain all of the phenomena. When you consider reflection and refraction, these can be easily explained by ray optics. These can be really easily explained by ray optics. But when you consider interference, diffraction and polarization, these can be easily explained by wave optics. So in the first part of the chapter, we'll focus more on reflection and refraction. And then as we move on, we'll study more about the wave nature of light and how the wave nature corresponds to the properties of interference, diffraction, and polarization. So with that, let's start our first lecture. So first lecture. So with that let's start our first lecture. And in the first lecture, let's talk about light and the property of reflection. So these are the sections that we're going to discuss. So first we'll talk about what are the characteristics of light. Number 2, then we're going to talk about mirrors, and we'll discuss the two types, flat mirrors and curved mirrors. And we'll also see how this can explain the common concept of image formation. What is an image and how does it form? Next, finally, we'll talk about color and polarization. So how is color formed and how can you polarize a certain amount of light? So let's start with the characteristics of light. So the objectives in this class, once you complete this lecture, so you should be able to identify the components of the electromagnetic spectrum. You should also be able to calculate the frequency and the wavelength of electromagnetic radiation. You should be able to recognize that light has a finite speed, and you should be able to describe that how brightness of a light source is affected by distance. So let's start with electromagnetic waves. Light is a form of electromagnetic radiation. Why is that the case? An electromagnetic wave is a wave that generally consists of oscillating electric and magnetic fields, which then radiate outward from the source at the speed of light. So what does that mean? So if you consider a wave, you can draw a wave in simple sense. If you consider a general wave, a wave generally has peaks and troughs, so it's easy to understand a wave. But a light wave is a combination of two fields. You have an electric field and a magnetic field. So what happens here is that if you consider this to be the electric field, so E bar, then there should be a magnetic field. The magnetic field then is generally perpendicular. So the magnetic field is then perpendicular to So if this goes upward, so for example, if you consider the light wave, the light waves are pointed up, while the magnetic field is perpendicular to the actual light wave. So you can consider this somewhat like this. So the idea here is to think that the magnetic field and the electric field are perpendicular to each other. What does that mean? So if you look at it from here, so what is happening is the view will look somewhat like this. On the top, so in the perpendicular direction, in this direction, we have the electric field. So the electric field is operating in this direction with the mean point right here. So this is the mean position, while the magnetic field is perpendicular to this, right? So it's perpendicular to this in this direction. So where it's oscillating front and back, the magnetic field will look somewhat like this. So this here is the magnetic field. Now the combination, so the combination of both magnetic field and the electric field, right, causes a motion. So this motion that is being caused, so it propagates perpendicular to both the vibrations. So what happens here is that both these waves are perpendicular to each other. This happens to be the propagation of the wave. This V bar represents the propagation of the wave. So this is how the wave propagates. So notice that all of them are in perpendicular directions to each other. So what happens here? That causes a motion. So that causes a motion perpendicular to both the electric field and the magnetic field. So this wave is called the electromagnetic wave. So we call this the electromagnetic wave. So understanding how light wave works is important because light is also an electromagnetic wave. So light itself is also an electromagnetic wave. Because it is an electromagnetic wave, it also has properties of an electromagnetic wave. But the problem here is that light in itself, it's not one wave. So because it does not mean that there is only one single wavelength of light, because it's a combination of waves of different wavelengths. So combination of waves of different wavelengths. This is called as a electromagnetic spectrum. So one way of looking at thinking about spectrum, so spectrum is a combination of waves. So it's a combination of waves. So we call light a electromagnetic spectrum because it contains a lot of forms of waves. So because this is the case, so we call this a form of electromagnetic radiation. So remember that what we call light is generally visible light. What we call light is generally visible light. What does that mean? If you take a light into its spectrum from the sun, so for example, let's consider sunlight, right? So if you consider sunlight can be classified into different spectrums. So what can we consider the spectrums to be? In the entirety of the entire spectrum that we saw, this small sliver of the spectrum is visible light. So this is the light that you can see. Right? This is the light you can see. And if you consider a scale of increasing wavelength, this value is about 0.4 micrometers, or let me write it as nanometers. It's about 400 nanometers to 700 nanometers or 750 nanometers, whichever is the case. So it's about 400 to 700 nanometers. In this, if we expand this a little larger, so if we expand this a little larger, you end up with a spectrum that has, so if you expand this into a spectrum, you have 1, 2, 3, 4, 5, 6, 7. So if it is split into 7 colors, right? So or 7 different wavelengths of light. So we can classify visible light into 7 different wavelengths. So the first light is violet. So the first light is violet. So you have the first light here is violet. Second light here is indigo. The third light here is blue. The fourth light here is green. The fifth light here is yellow. The sixth light is orange. And the seventh light is red. So to understand this, or to make it simpler, we give it the short form WebGR. So we call it WebGR. WebGR is violet, indigo, blue, green, yellow, orange, and red. So this is the short form given to all the wavelengths of light that are condensed into the visible light. So that are condensed into the visible light spectrum. What else are the waves that you find inside the spectrum? So let me write this visible light. Before visible light, you get UV rays. UV rays are ultraviolet rays. And before UV rays, you get X-rays. Before X-rays, you get gamma rays. Before X-rays, you get gamma rays. And after visible light, you get infrared spectrum. After infrared spectrum, you get microwaves. After microwaves, you get radio waves. So this is the entirety of the spectrum of light. So you have a combination of multiple amounts of light that are starting from a really small amount to a really, really large amount. For example, X-ray would start from around 0.1 nanometer to about 100 nanometers. So gamma rays have much lower than that. They generally have about 0.001 nanometer to 0.1 nanometer. When you take IR spectrum, it ranges from about 750 to about 1500 nanometers. So it generally goes to 1 millimeter. From 1 millimeter, it can go until 10 kilometers for radio waves. So microwave radiation is smaller, and then you end up with radio waves, which are much larger in length, right? So this is the idea behind the understanding of the spectrum of light. So this here is the electromagnetic spectrum. This here is the electromagnetic spectrum. So now let's look at each of these waves and let's understand how to classify them and what are the uses and what is the range of their wavelengths and frequency. So when you take the entire electromagnetic spectrum, let's start from the top where we talk about radio waves. Radio waves are generally of wavelength that are greater than 30 centimeters. They end up forming the AM and FM radio, and most of the television that you generally see comes from radio waves. So if you see the big antennas on the top of your house, those are basically receiving radio waves from satellites or can be from other beaming stations. The next one is microwaves. Microwaves range from 30 centimeters to 1 millimeter. They are used in radar technology, atomic and molecular research. They are also used in aircraft navigation, and most of the microwave ovens use this technology. Next, you have infrared rays. Infrared rays range from 1 millimeter to 700 nanometers. So they are used in molecular vibrational spectra, infrared photography, and physical therapy. So these are ways where you will see IR rays most commonly used. So an example of that would be your CC cameras, closed circuit cameras. So these basically use, if you see a CC camera at night, you would generally see a red dot. That red dot is basically emitting infrared waves to capture information that cannot be seen by visible light, because visible light cameras can only capture visible light. But if you want to capture video at night, you need to have something else. That here is the infrared waves. Next, the common ones that we know is wild visible light, which ranges from over 700 nanometers to 400 nanometers. Right? So they are used in visible light photography, optical microscopy, and optical astronomy. Next, UV light. UV light is generally from 400 nanometers to 60 nanometers. So they are generally used for sterilization of medical instruments, identification of fluorescent minerals. So UV light is also another where you see sterilization. The reason it's used for sterilization because UV light has really high frequency. So really high frequency. What does that frequency do is it damages the DNA and RNA of many microbes. So it damages the DNA and RNA of microbes so that they don't live and they'll die off. So this is generally a way for sterilization. The next one is X-rays. X-rays range from 60 nanometers to about 0.0001 nanometers. They are generally used for medical examination of bones, teeth, vital organs, and they are also used to treat some types of cancer. So one another use of X-rays is to detect anomalies in materials that are formed. For example, if you're in a manufacturing plant, for example, let's say if you have a manufacturer that's making surgical blades, and if you want to know if your surgical blades are good enough, so to make sure that there is not much, there's not many holes inside it or there is not much damage inside it. So they make sure to check random samples using hard X-rays. So what do hard X-rays do is they'll show if there is any defects inside the metal. And the final one are gamma rays. Gamma rays are used generally from 0.1 nanometers to 10 power negative 5 nanometers. They generally used for examination of thick materials for structural flaws. They are also used for treatments of some types of cancer, and most common use of this is food irradiation. So what does this do is basically damages microbes and extends shelf life. So it extends the shelf life. So these are the uses. So these are the common uses and the range of wavelengths of an electromagnetic spectrum. One other thing that you would have noticed is that as we come down the wavelength, as we go backward in terms of the wavelength is decreasing. So as lambda decreases, the frequency starts increasing. So focus on this fact. We'll come back to this again. Now, what is the relationship between an electromagnetic wave's frequency and wavelength? So we call it the law of electromagnetic radiation. What does that law state? Is that for any electromagnetic wave, the speed of the wave is constant. So the speed of the wave is always constant. So the speed of an electromagnetic wave is always constant, and that value is 3 times 10 to the power 8 meter per second. If you would have noticed this value, it's also the speed of light. The reason it is that value is because light is also a form of electromagnetic radiation, so their speed is always constant, whatever the case is or whichever the light is, right? Which means that a gamma ray has the same speed as that of a radio wave. But what differentiates a gamma ray and a radio wave is they're differentiated by their frequency and their wavelength. So if you remember the common concepts of a wave, so we already talked about a wave in general. So when you look at a wave has crests and troughs. So which means that when we talk about two crests of a wave, we called it lambda. So we also consider this to be one single cycle. So what is one single cycle? If it completes one single this is considered to be one cycle, right? What is wavelength? So what can we call wavelength? Wavelength is the distance between two crests or two troughs, right? So this is the wavelength. So this is the wavelength, right? Or one another simple way is the length of one cycle. So for the length of one cycle, we consider it to be wavelength. The other definition we want to know is what is frequency then? Frequency is a factor that determines how many cycles can a wave make in 1 second. So we talked about cycle. This is one cycle. Frequency, the definition of frequency is the number of cycles per unit time. This unit time is generally used as second, so which means that cycles per second is the common unit for measurement of frequency. So to make it simpler, cycles per second is called as hertz. So it's named after the scientist and the symbol is Hz. So 1 hertz represents 1 cycle per 1 second. This is the idea behind 1 hertz. Now we talked about wavelengths and frequency. Why is it that in an electromagnetic wave the speed is constant and they are only changing in? So speed here is always constant, which means for a gamma ray and a radio wave, both their velocities are both their speeds are the same, which means that the only thing that is changing is either lambda is changing or the frequency is changing. But if both of them have the same speed, we know that the values these two are changing. So which means that here we can also write the law of electromagnetic radiation. C can be written as the product of frequency and wavelength. This is the law of electromagnetic waves. So basically says that the speed of any wave is the product of its frequency and wavelength. So this product is what ends up becoming the speed of the wave. Now, how can we say that this is exactly the value? The reason it's same for both gamma and the radio waves is because when you consider gamma and the values for frequency and wavelength, so let me write it separately. So when you consider the values for frequency and wavelength, right? So the value for a gamma ray, the wavelength is really small. It goes down. So the frequency is generally high. But for a radio wave, the wavelength is high, the frequency is low. This is the reason why they can always have the same speed. So they can survive with the same speed. Right? And that value is 3 times 10 to the power 8 meter per second. The reason we say that this is speed is because we are talking about a wave. So we do not represent the value by a velocity, because velocity is not something that we use in terms when we consider light. Because there is always an argument saying that velocity is something that you can use for only for particles. So that's why we use the name speed of light and not velocity of light. Next. So each of these electromagnetic waves, you can approximate them to be rays. Why is that the case? Let's take a simple example. Let's say you have light rays that are going out from a source. For example, let's consider that you have a single source at the source. Now 1, you have 2, and you have 3, you have 4. So this is an idea of how light emanates from a source. Right? So light emanates from a source. So if you consider this to be the source that's emitting the light, source emits lights in the form of waves. So we already told that it's an electromagnetic wave. But why do we call it a ray? So why are we approximating the wave into a ray? Now when you take a small segment of this source, and really expand it, what you notice is that when you look at a really far away distance, the actual waves end up becoming straight lines. So this basically it converts from a spherical waves into a plane waves. So they convert from a spherical waves into a plane waves at long distances. Why do we say long distances? For example, when you're nearly in front of the light itself is really small wavelengths with really high frequencies sometimes. So but when you consider visible light has a lambda value that ranges from 400 nanometers to 700 nanometers. So which means that the wavelength is really small. So these are really close to each other. So when they come near each other, what you can do now is you can approximate a line or a tangent. You can draw the tangent directly from the center of the wave, propagating outside to the wave. So this basically is the concept of drawing tangents. So basically what you're doing is through each and every center, you're passing rays. Now when you take these rays also and approximate it into the entire plane, what you notice is that these are nearly parallel to each other. They are not exactly parallel, but when these lines are drawn at really small, when you expand the wave to a really large scale, you notice that it becomes straight lines. This here is called as the Huygens wave approximation. So this here is called as the Huygens wave approximation. So this type of analysis, when you consider waves to be rays, so you can approximate to be rays, this is called as the Huygens principle. So we call this the Huygens principle. Now, when we talk about Huygens principle, we are basically approximating waves as rays. What can that do? It doesn't do much, because the wave front will stay the same. But what is happening basically is we're approximating it to be a ray. So that's why we call them rays. So the rays here are always drawn perpendicular to the wavefront. Always remember that whenever we drew this, we call this a tangent. So a tangent is a line that's always perpendicular to the point of intersection. So which means that at this point, at all of these points, they have a 90-degree angle. So all of them have a 90-degree angle. At every point where they touch, they always should have a 90-degree angle. That's what is defined as a tangent. So which means we always have to remember that this is an approximation of a wavefront, which means that they are always drawn perpendicular to the wavefront. This can also explain some more big concepts such as illuminance. So what happens in terms of illuminance? Illuminance, think of it like how bright is the light as you go far and far away from the source. So as you go far and far away, so it decreases, the illuminance of the light decreases square of the distance from the source. So as you go far and far away, the intensity of the light or the illuminance of the light reduces really with a high value. The rate at which the light is emitted from a source is generally called luminous flux and is generally measured in a value called lumen. Now, at 1 meter, if the illuminance was considered to be 1 unit, then at 2 meters, it becomes, for example, if you consider 1 unit here, it becomes 0.25 units. Here, when it comes to 3 meters, it splits into 0.1, so 11 something, so 0.11 units. So there is a large reduction in the value as the distance progresses. This reduction is proportional to the square of the distance. So this is proportional to